Hey everyone, in this video we're going to talk about the third part of section 5.2, talking about rational exponents and radicals. So basically where we're going to start with this is we're going to be combining radicals or rational exponents, and the big idea here is that you have to get them to match perfectly in order to do that. So for example, we could kind of compare this to the idea if I said to you, what is 2x plus 5x? Well, you would say, I'm comparing x and x. I have two x's. I add 5 more to it. So we'd get a final answer of 7x. It's going to be that same exact idea, but just instead of having a variable of x, what it's going to be is having just a radical in it or a rational exponent. So looking at this first example, I have the fourth root of 10 plus 7 fourth root of 10. So it's basically like saying you have 1 fourth root of 10, you add 7 more to it, gives you a total of 8 fourth roots of 10. Key idea here is the number under the radical and the root match. So we add the coefficients out in front of them. 1 plus 7 is 8, 8 fourth roots of 10. Same idea if you have rational exponents. We have the same base of 8, and both of those 8s are raised to the 1/5 power. So instead, we're going to be focusing on the numbers outside, this 2 and this minus 10. So 2 minus 10 is going to give us negative 8, 8 to the 1/5 power. Once again, you're focusing on the coefficients on the outside, you're just subtracting. Now, the problem with something like number 3 is you don't have the same number that's underneath the radical. You do have the same root, which is good, but we have a 54 and we have a 2. So what we're going to do instead is we're going to almost treat this like it's 2 separate problems. So you can take a piece of paper, you can take a sticky note, something, and all you're going to do is you're going to cover up, and I'm going to use this box to help us. You're going to cover up the right side of your problem, and we're only going to focus on the cube root of 54. And we're going to try and break this down as far as we can get it to go. So I start and I look for the biggest cube that is going to divide into 54. The biggest perfect cube that divides into 54 is 27. So that's the cube root of 27 times the cube root of 2. 27 times 2 will bring us back to 54. Remember, we're ignoring the right side of our equation until the very end. And then we keep simplifying. So after that, I have a plus, but I'm going to forget about what's underneath that box. So the cube root of 27 is going to give us 3. So that's 3 cube root of 2, and then a plus. Now, we can't break this down any further. So what we're going to do instead is we're now going to cover everything on the left side, and we're going to focus on this cube root of 2. The cube root of 2 can't be broken down anymore, so instead we're just going to bring it down in each step. So I have the cube root of 2 to the right of the plus sign, and the cube root of 2 to the right of the plus sign. Because now, if you take that box away and we focus on the problem as a whole, you can see that I have the cube root of 2 for both of these. So now I can just combine it like normal. And if it's helpful to you, this is not just the cube root of 2, but 1. cube root of 2. So now I can add, I have 3 plus 1 is going to give us 4 cube root of 2. Okay, we're going to follow this same idea for problem 4. When I look at this, I have the cube root of 40 and the cube root of 135. Once again, we're going to cover up the right side of our equation, and we're going to focus on just simplifying each side before we combine it as a whole. If I look at 40, the biggest perfect cube that goes into 40 is 8. So I have a 9 being multiplied on the outside. That's 9 times the cube root of 8 times the cube root of 5. And then I have a minus after. All right, we break it down a little bit more. The cube root of 8 is 2. So that's 9 times 2 times the cube root of 5. Or 9 times 2 is 18. 18 cube root of 5. We can't break down the cube root of 5 anymore, so now we're going to do the exact same thing, but we're going to focus only on the right side of the equation. And obviously, if you have a piece of paper or your hand or calculator, it's going to cover all of this up a little bit better. So following that same idea, I'm going to break down 7 cube root of 135. The biggest perfect cube that goes into 135 is 27, and it's 27 times 5. That gets us 135. The cube root of 27 is 3, so we have 7 times 3 times the cube root of 5. 7 times 3 is going to give us 21. 21 cube root of 5. Now, like we did before, we can uncover the entire problem now that we're at our most simplified, and we can focus on combining these. So I have 18 on the outside and a negative 21. My root and the number under my radical match, we can combine like normal. 18 minus 21, that's going to give us negative 3 times the cube root of 5. The second type of example that we're going to talk about is how to simplify these expressions. Your goal is to get each of these to be written with an exponent of 3 or a multiple of 3. So what I mean by that is we are focusing now on our root of 3 on the outside. And I want everything that I write under this radical to be raised up to the 3rd power. So what I'm going to do is I'm going to rewrite this. That's the cube root of 64 is 4 to the 3rd. 3 goes into 6 2 times, so I can write y cubed twice. And then 3 goes into 7 2 times, so I can write z cubed twice. But then 3 plus 3, you need one more z to get it up to 7. And then what we're going to do from there is whenever your power matches your root, you're able to cross it out and bring it out in front. So 4 to the 3rd comes out front as 4 because power matches root, they cancel. Y cubed comes out as y. Y cubed comes out as y. Z to the 3rd comes out as z. Z to the 3rd comes out as z. The only thing that you do not get to get rid of is this z under here because it does not have a power of 3. So you have to leave it underneath the cube root. So you leave it as the cube root of z. Just to clean this up a little bit, we want to write this one final time. This is 4, 2 y's on the outside, 4y squared, 2 z's on the outside, z squared, times the cube root of z. For our final answer. We're going to do the same idea when we have division. So I'm going to write this as the 4th root of x to the 4th over the 4th root of, and then 4 goes into 8 2 times, so I can write y to the 4th twice. And then same idea, when your power matches your root, you get to bring it outside. So x to the 4th gets to just come out as x. Y to the 4th comes out as y. Y to the 4th comes out as y. So our final answer is x over y squared. Remember, you're trying to get every number and variable to be written as that number or variable raised to whatever your root is. Couple more examples of these just to help a little bit. We will focus on number 7. Number 8, if you want to look through that, the work for that one, it is posted on Canvas, filled out. So try some of these that we don't go over and make sure you fill them out. So I have the 5th root. So I'm trying to write things as something to the 5th. 4 can be written as 2 squared, but because it's not a power of 5, it's really not helpful to us. So we're just going to rewrite it as 4. 5 goes into 8 once with 3 leftovers. Then you have to write it a cubed as well. 5 goes into 15 perfectly, and it goes in 3 times. So I get to write b to the 5th 3 times. And then obviously if you just have c to the 5th, that gets written as well. So whenever your power matches the root, cross it out and bring it out front. A to the 5th comes out as a. 1, 2, 3 b's get to come out. And then c to the 5th also gets to come out. What you're left with is the 4a cubed. And then we clean it up just a little bit. This is a, and then we have 3 b's, so b cubed c times the 5th root of 4a cubed. The 4 and the a cubed have to stay underneath the radical because they do not have a power of 5. Now, something like number 9. Huge red flag is that we have a radical in our denominator. The other issue is that 3 does not go perfectly into 8. Our big thing is that this 8 needs to become a multiple of 3. That power of 8 needs to become a number that is a multiple of 3. So for example, you think about multiples of 3. That's 3, 6, 9, 12, 15, etc. And you need to find the one that is bigger than 8, but closest to 8, which in this case would be 9. 8 plus blank equals 9. Because the number that goes in this blank is 1, that means that we have to multiply by y to the first in order to rationalize our denominator. So we have x over the cube root of y to the 8th. We're going to multiply numerator and denominator by the cube root of y, because that's y to the first. Now, in doing this, we are going to get x cube root of y over the cube root of y to the 9th, because our rules of exponents say that we're going to add 8 plus 1 is 9, which then, if we think about it, focusing on the denominator, 3 divides into 9 3 times. That's x cube root of y over y to the 3rd, because you can break up this y to the 9th as y cubed, and y cubed, which is why it comes out in front as y cubed, because you have 3 of them. So our final answer is going to look like that. Now, this next example, what we really want to be focusing on first is ignoring the radical, and I want you to just simplify what's on the inside. We will add the radical back in at the end. What we're going to do to simplify this is we have 405 divided by 5, and then rules of exponents say that if we have like bases, like we do in the x's, we subtract the exponents. That's 3 minus negative 1. And the same thing with the like bases of y. That's y to the negative 3 minus 1. Obviously, what's still around this is the 4th root symbol. So, like I said, we're going to ignore that for a while. Breaking this down, 405 divided by 5 is going to give us 81. X to the 3 minus negative 1 is going to give us x to the 4th, and then y to the negative 3 minus 1 is y to the negative 4th. Once again, what's still around this is your 4th root symbol. Our problem is we don't like to deal with negative exponents. So in order to make an exponent positive, I want to move it down to the denominator. That's 81 x to the 4th over y to the 4th. And then same thing like we've been doing, 4th root symbol around both of those. And from there, it's pretty easy. We can just break it down. The 4th root of 81 is 3. The 4th root of x to the 4th is x. And the 4th root of y to the 4th is y. Two more examples and we're done. The only difference in example 11 compared to what we did on the front side is that I'm giving you a variable underneath the radical. You still want to look for two things. Is under the radical the exact same, which it is, and is the root the exact same? If there's no number, we know the root is automatically the square root, a root of 2. From there, you're going to do 5 plus 6, which is 11, or more specifically, 11 radical y. 12 is one of those ones where they don't match, and we're going to have to simplify as far as we can. So if I focus and I cover up with a box again, looking at this problem, I have 12 times the cube root of 2z to the fifth. I'm focusing on the inside part. I don't care about the outside right now. 2 is not going to break down, obviously, because I can't rewrite 2 as something to a power of 3. But what I can do is I can rewrite my z to the fifth as z cubed and z squared, because 3 plus 2 will bring us back to 5. Then, because you have a root of 3 and a power of 3 on that first z, I can bring it out front as just a z. So that's 12z, and then you're left with underneath the cube root of 2z squared. After each step, we have a minus sign. You can't break it down any further, so I'm going to focus on the right side of my equation next. I have a z on the outside. Obviously not going to be able to rewrite z squared at all, but I want to try and rewrite 54 as a perfect cube times some number. 54 can be rewritten as 27 times 2, because 27 times 2 is 54. 27 is a perfect cube. And then I also have this z squared. Now I'm able to take the 27 out in front as a 3. Cube root of 27 is 3. So I have 3z times the cube root of, and you're left with 2z squared on the inside. We can't simplify that anymore. Now we look at our problem as a whole. Now when we look here, I have the same thing under the radical, and both radicals have a root of 3. We can go ahead and combine. So on the outside, you have this 12z minus 3z. That's going to be 9z. And then more specifically, 9z times the cube root of 2z squared. Final answer for this one. So once again, there are a couple student practice problems. I would really encourage you all to check those out. They are filled in one of your files on Canvas. I think it's going to be super helpful for you to try a couple of those on your own.